So I'm audible. So in the last class, I left a numerical for you people. You were supposed to calculate passing through a sphere of radius 2r. Ken's, we are doing Gauss law right now. Ken Saleh. This is basically first class of Gauss law. Okay, so Froza, Fatima, and Jubaina, did you got the answer of the homework question?
I got Q by epsilon.
Q by epsilon naught. So, and others all got the same answer. Yeah. The answer is Q by epsilon naught. If you all got Q by epsilon naught, then I will not solve this problem further. So you all got Q by epsilon naught, Afroza, Fatima, Jubaina. Okay. So I'm not solving it. Next, let's move on to Gauss law. Let's move on to Gauss law. Now, Gauss law says if you have a closed surface of any arbitrary shape or size, it could be a sphere, it could be a cylinder, or closed surface of any arbitrary shape or size, and you place a charge inside that closed surface. If you calculate electric flux through the closed surface, electric flux through closed surface, so this is the definition of flux. Flux through the closed surface is closed integral of E dot ds. Now for this particular surface, this closed integral is tough. This integral of df would be tough. But if you perform this integral, then the end result would be Q by epsilon naught. End result would be Q by epsilon naught. We have already done this thing for sphere. We have solved two sphere. A sphere of radius r. We place the charge Q at the center. The flux comes out to be Q by epsilon naught. Then we just double the radius of this sphere. We take the radius of sphere to be 2r. We place same charge Q at the center. And this comes out to be Q by epsilon naught. Yes, Fatma, this result is same for any shape, any size. The only thing that matters is your surface should be closed surface. So if you have a closed surface of any arbitrary shape, any size, and you place a charge Q inside that closed surface, then electric flux passing through that surface is Q by epsilon naught. And I'm writing this as Q enclosed. Q enclosed means charge inside the closed surface. So that's Gauss law. That's Gauss law. So Gauss law says that electric flux through a closed surface is 1 by epsilon naught times the charge enclosed by the surface. This is Gauss law in electrostatic, that electric flux through a closed surface is 1 by epsilon naught times the charge enclosed by the surface. So this is the statement of Gauss law. Next, we have some characteristics of Gauss law. The first thing is it is independent of shape and size of surface. Gauss law is quite independent of shape and size of the surface. So whatever be the shape or size of surface, flux would be same. Means you can have a sphere, and if you place a charge q at the center of the sphere, then the flux through the sphere is q by epsilon. This is sphere of radius r. Even if I double the radius of this sphere, I take this as 2r and place same charge inside that sphere, then flux will again be q by epsilon. Closed surface. If instead of sphere, I take a cylinder, inside that closed surface, so flux through that surface is again q by epsilon. If instead of cylinder, I take any arbitrary shape and put a charge q within it, then again the flux through the surface is q by epsilon. So this results depends only over the shape and size of the surface. Sorry, only on the nature of closed surface and the charge enclosed. It's absolutely independent of shape and size of surface. That's the first thing. The second important thing about Gauss law is uh, outwards flux is positive. Outwards flux is positive, and inwards flux is negative. Inwards flux is negative. Flux which is moving out of the closed surface is positive, and flux which is entering the closed surface is negative. So if I take a closed surface, I put a positive charge, then electric field lines will move out of the surface. These field lines will move out of the surface. So the flux is simply plus q by epsilon. This is flux q by epsilon. And if I put a negative charge here, minus q, then flux will enter. Flux will enter. And this inwards flux is taken as negative. Flux will be minus q by epsilon. So, is it clear up to this point, or you have some doubts? Okay. Fatma, Ken Saleh, are you getting it? Ken, you have missed basically the last point. Okay. Jubaina, the last point says that if a flux is moving out of the surface, say you take a point charge, a positive charge, and you place that positive charge inside the closed surface, then electric field lines will leave the surface. Electric field lines will move out of the surface. So if field lines are moving out of the surface, then we consider that flux is positive. And if you, instead of a positive charge, if you take a negative charge and you place that negative charge inside the closed surface, then instead of moving outwards, field lines will enter. Field lines will enter in the closed surface and your flux will be negative. So flux moving out of the surface is positive, while flux moving inwards is negative. Just note it down. Yeah. It's because if you have a positive charge, then field will move away from the positive charge. And if you have a negative charge, then field lines will move towards the negative charge. So, shall I rub it? Ken's, shall I rub it? The next is, say you have a closed surface and some feed lines are crossing this closed surface. Feed lines are just crossing the closed surface. Crossing means they are entering the surface and then moving out. If we calculate total flux, then if you have feed lines, Afroza, how would you calculate flux if you have feed lines? What is definition of flux in terms of feed lines, Afroza? How would you calculate flux in terms of feed lines, Afroza? Fatma, what is definition of flux in terms of feed lines?
The number of field lines
Yeah.
is
Afroza, in terms of feed lines, flux is simply the number of feed lines crossing the area. So if this is the area and 3 feed lines are entering, then the flux is -3. It's just count the number of feed lines perpendicular to the area. 3 feed lines are entering in the closed surface. Entering flux is considered as negative, so that's -3. Then 3 feed lines are leaving this closed surface. Flux is simply +3. -3 is entering and +3 is leaving. So the total flux is 0. So the total flux which is crossing this closed surface is 0. So simply if feed lines are crossing a closed surface, then total flux through the surface is 0. The reason is simple, because the number of feed lines which are entering the surface are exactly equal to the number of feed lines which are leaving the surface. That's it. The next property. Like say you have this closed surface, and in this closed surface I put a dipole. Within this closed surface I put an electric dipole. Juvena, what should be the total flux? If inside this closed surface I just put a dipole, then what should be the flux?
0.
0. Why?
Say opposite charges are there, minus and positive.
Charge is 0, right? So if you have a dipole, then you can say that your Q enclosed is simply plus Q minus Q, which is 0. So flux is 0. Net flux through this closed surface is 0. The next is so if you place the dipole inside a closed surface, the net flux through the closed surface is 0. The next property is charge outside the closed surface will not contribute to flux. So if you have a charge which is outside the closed surface, then that charge will not contribute to flux. Charge outside the closed surface will not contribute to flux. So if you have a closed surface, there are charges like Q1, Q2, Q3, Q4. There is one charge Q4 which is absolutely out of the closed surface. Then this Q4 will not contribute to flux. And the flux will be, it's simply Q1 plus Q2 plus Q3 by epsilon. That is it. This Q4 will not contribute to flux. Charge outside the closed surface will not contribute. Please note it down. So, shall I rub it? Okay, so that was about Gauss law. Next, we have some applications of Gauss. Okay, before application, let's solve one more numerical. Say you have a sphere, and inside this sphere, we placed a charged rod. The linear charge density of the rod is its sum kx. The length of the rod is L. Calculate flux through the sphere having a charged rod of length L. So if you have a rod of length L, a charged rod of length L, you're supposed to calculate the flux through the sphere. Try to solve this problem. Flux is Q by epsilon naught. Charge density is given, and you can check that this charge density is non-uniform. First of all, calculate the net charge inside the sphere, and then using Gauss law, calculate flux. Solve this numerical. Yesterday we did a numerical on this non-uniform charge density. We have calculated the total charge. No, Fatma, it won't be LKX epsilon naught. No. Just check some questions on linear charge density. We did two questions of linear charge density. The second numerical. In the second numerical, we take this non-uniform charge density and we have calculated the total charge. Just check that numerical. Calculate total charge using that non-uniform charge density and then flux using Gauss law. Jubena, Afroza, Ken Saleh, answers. Limit would be from 0 to L simply. Simply from 0 to L. Total length is L, just take it from 0 to L. No answer. See, here charge density is non-uniform. So for non-uniform charge density, your lambda is simply dq over dx. Next, you can write your dx as dx is lambda dx. So charge on length L, for charge on length L, Q is integral of lambda dx. The limit is from 0 to L. This is from 0 to L. Lambda is kx dx. This k is constant. You can take this constant out of this integral sign, and this is 0 to L. It's x dx. This is k. So this is x to the power 1. You can integrate this x to the power 1. It's x square by 2. It's 0 to L now. So the total charge is, it's k by 2. It's L square minus 0 square. So the total charge inside the sphere is, it's k L square. Once you have this total charge, so is it clear up to this point? This charge enclosed, is it clear? Afroza? Okay. Oh, once you have charge enclosed, then Giovanna, how would you calculate the flux? Flux through the sphere. If you have charge enclosed, how will you calculate flux?
X equal to
Yes, Giovanna.
like Q by epsilon.
Q by epsilon. So that's flux is Q over epsilon naught. So that is K L square. This is how we calculate. So done. Shall I have it? There are few more questions on Gauss law. Like there is one. Say you have a cube. This cube is a closed surface. It's a cube. Inside this cube, you place a charge q. So calculate a charge q is placed at the center of q. Calculate, the first part is flux through the cube. Flux through the cube. And second part is flux through each face. Through the cube, and second part says flux through each face. So Afroza, what should be the answer of first part? Have a cube, a closed surface. Answer of first part. Yes, right. The charge enclosed by the cube is q. So this is flux. Flux is q by epsilon. In the second part, you need flux through each face. So altogether, this cube has 6 faces. Altogether, this cube has 6 faces. Flux through each face. So if I'm saying that flux through the cube is Q epsilon naught, can I say that flux through 6 phases? Flux means field lines. Field lines are passing through each and every phase. So if I'm saying that flux through the cube is Q epsilon naught, that means I'm saying that flux through all 6 faces of the cube is 6 by epsilon. So flux through all 6 faces is Q by epsilon. So this is it. So through all 6 faces of the cube, the flux is Q by epsilon. If you need flux through one phase, okay. Fatma, at the center of the cube, we placed a charge cube. The flux is passing through the cube. Flux is passing through the cube means electric field lines are passing through each face of the cube. Right? If I'm saying that flux is passing through the cube, so cube means 6 faces, 6 squares. So if I'm saying that flux is passing through the cube, that simply means flux is passing through 6 squares. So through the all 6 squares, flux is passing. So altogether 6 faces, the flux is Q by epsilon naught. Now you got this thing. If I'm saying that flux through the cube is Q by epsilon naught and cube has 6 faces. So I can write this as through 6 faces, flux is Q by epsilon naught. Fatma. So Fatma, what should be the flux through one phase? Through 6 faces, it's Q by epsilon naught. And what should be the flux through one phase?
Q by epsilon naught only.
Again, Q by epsilon naught. Through 6 faces, it's Q by epsilon naught. I'm asking about one phase. Equal flux is passing through all phases. So through all 6 phases, the flux which is passing is Q by epsilon naught.
Q by epsilon naught by 0.
Q by epsilon naught by 6. Altogether, through these 6 phases, the flux which is passing is Q by epsilon naught. So through one phase, the flux should be Q by epsilon naught by 6, right? Is it clear? Just unitary method. I'm using just unitary method. Sorry. So through one phase, the flux which is passing is Q by, or I can write this as 1 by 6 into Q by epsilon. Afroza and Jubaina, is it clear?
Yeah.
So if charge is given, this is how we calculate flux through each phase. Okay, just please note it down. Yes, Fatma, this is the final answer. Q by 6 epsilon. So through the whole cube, the flux which is passing is Q by epsilon naught. Through one phase, the passing flux is Q by 6 epsilon. The next question is, instead of Q, say you have a square. You have a square. Each side of the square is A. From the center, this is question of NCERT. From the center of square to a height A by 2, we place a charge Q. So each side of the square is A. From a height A by 2, from the center of the square, we just substituted a charge Q. You're supposed to calculate flux through square. You need to calculate flux through this square. It's like, say, this is the square. Each side of the square is A. From a separation A by 2 from the center of the square, here I place the charge Q. You're supposed to calculate flux through the square. So the question is, can I use Gauss law to calculate flux through the square?
No.
Yes or no?
No.
No, it's not a closed surface. We can't use Gauss Law. So for these type of problems, try to construct a closed surface using this square. Add some more squares and try to make a closed surface. So can you make a closed surface out of this square by just adding more squares? Just tell me the minimum number of squares that you would need to make a closed surface out of the square.
Another 5.
Another 5 square, right? Then what would be the final shape?
Cube.
What would be the final shape then?
Cube, right?
Cube, right? Yes. So in this question, just add few more squares. So add 5 more squares and get a cube having charge q at the center. Having charge q at the center. So charge q is placed at a separation a by 2 from the center of the square. You're supposed to calculate flux to this square. To calculate flux to this square, we first made a closed surface. We add 5 more squares and get a cube having charge q at the center. So if we add 5 more squares, the shape will look like. Please use your name. This HLO doesn't sound a valid name. Please use your real name, otherwise I'd put you in the waiting room. Please edit your name, otherwise I'll put you in the waiting room. So this is Q, and we placed a charge Q at the center of it. So if I add 5 more squares, then you will get a closed surface, which is a cube, and the charge Q will lie at the center of it. Now, you need to calculate flux through the same one side of the cube, which is a square. Can you guess what should be the flux through this square? Say,
Yes.
in question, you just have a square of side A from a separation A by 2 from the center of the square. We place the charge Q. You're supposed to calculate flux through this square. But we cannot use Gauss law for the square since square is a open surface. So we add 5 more squares, we get a cube, and we place the charge cube at the center of the cube. Charge Q at the center of the cube. Now you can easily calculate the flux through the cube. So what is the flux through the cube?
Q by epsilon.
It's Q by epsilon naught. Can I say that flux through cube means, yes, flux through 6 squares, right? Cube have 6 squares. Through 6 squares, flux is Q by epsilon. Flux through 1 square is 1 by 6 Q by epsilon. This is problem of NCERT. Maybe some additional question of NCERT. Please write it.
So why can't we find flux through open surface using for square we can use E dot S, right?
Yeah, we can do E dot S, but actually the value of field over the surface of square will continuously change. For this point charge, the field over this point and over this point would be different. So if you are calculating field due to this charge over the surface of square, then the value of field would be different. You can't use directly this expression. You will have to use integral of E dot ds. First thing, for the square, the value of field is different at different points. So you can't directly use E dot ds. This is valid only if field is uniform. Here field is non-uniform. So you will be using closed integral of E dot ds. Now the issue with this integral is you don't know how to solve the surface integral for a square. We just have learned surface integral for a sphere, surface integral for a cylinder, curved surface of cylinder. We really don't know how to calculate the surface integral for a square. This problem will be this particular approach will be very complicated. We have to learn exactly how to calculate the surface integral. The surface integral will not be just a square. So just to avoid this surface integral, I'm using Gauss law. I'm making a closed surface, putting a charge over the center, and then calculating the flux through 6 squares and then through 1 square. If you want to solve this problem using this approach, then you have to learn this surface integral, how to perform surface integral for a square, which is a lengthy. That's why I'm not using this approach. Fatma, is it clear? Just to avoid this surface integral, I'm not using E dot ds. So shall I rub it? Afroza, Lubena. Afroza, shall I rub it? Okay, after this, we have some applications of Gauss law. Applications of, just one more question. Just one more question on Gauss law. Say you have a hemisphere. This is hemisphere. At the center of the hemisphere, you place the charge Q. Can you calculate flux through the hemisphere? Calculate flux through hemisphere. Flux through hemisphere. Having charge Q at center. So you're supposed to calculate flux through the hemisphere having charge Q at the center. Try solving this problem. You can't even use Gauss law for a hemisphere. You have to do some construction. Solve this thing and report your answer in chat. Answers. No answer. See, Afroza, this hemisphere is a closed surface or an open surface? It's hemisphere, hemisphere. It's like a bowl. It's like a bowl, a hemisphere. It's an open surface. You see, hemisphere is, if you take a bowl, it's open from above now. This hemisphere is an open surface. So, can you make it a closed surface, Jubaina?
Yes, sir.
How?
Using another hemisphere,
Yes,
construct another hemisphere.
yes. Just by putting one more hemisphere, you can make it as a closed surface. This is closed surface. Just add one more hemisphere. Add one more hemisphere. Just add one more hemisphere. So when you add one more hemisphere, then it becomes a sphere. And sphere is a closed surface. So flux through sphere is Q by epsilon naught. So Fatma, what is flux through this hemisphere? Fatma, if flux through the sphere is Q by epsilon naught, what about flux through hemisphere?
Q by epsilon naught by 2.
Yes, Q by 2 epsilon naught. It's half. Because a sphere have two hemispheres. If I am saying that flux passing through the sphere is Q by epsilon naught, that means altogether flux through two hemispheres is Q by epsilon naught. So through one hemisphere, flux will be simply Q by 2 epsilon. That's it. Okay, please note it down. The next is application of Gauss law. Application of Gauss law. So we have few applications of Gauss law. The first application is electric field due to infinite plane sheet. Due to infinite plane sheet. Next is electric field due to infinite line charge, or you can say wire or rod, something which is one dimensional. Then third application is electric field due to sphere. So these three applications of Gauss law are in your syllabus, and this is the most important topic of first chapter. In first chapter, the weightage of 3 marks is reserved for this application of Gauss law. So this is electric field due to infinite plane sheet, electric field due to a line charge wire or rod, or electric field due to a sphere. Let's calculate electric field due to infinite plane sheet. Before calculating field due to infinite plane sheet, there is one mathematical construction which is known as Gaussian surface. There is one simple mathematical construction which is known as Gaussian surface. Gaussian surfaces are basically closed surfaces. They are mathematical. These are geometrical surfaces used to simplify this integral. Just to simplify this integral, we use some geometrical shapes which are known as Gaussian surface. We have some criteria to choose Gaussian surface. First, it should be closed. Gaussian surface should be closed so that you can use this close sign. The second is electric field should be uniform. Electric field should be uniform. The second criteria. Fatma, this may have got cancelled, but for capacitors, we have to solve this flux due to the sphere. We have to solve this sphere. Without this sphere, we can't do capacitance of a sphere, nor we can do potential of the sphere, which is itself in the syllabus. Right? So we can't really skip this sphere. So electric field should be uniform. The third is electric field should be parallel or perpendicular to Gaussian surface. So electric field should be either parallel to Gaussian surface or it should be perpendicular. Now, depending upon the type of charge configuration, you can have different types of Gaussian surface. If your charge configuration is spherical, for spherical charge configuration, your Gaussian surface is spherical. Gaussian surface is spherical. So if your charge distribution is spherical, then your Gaussian surface is spherical. If your charge distribution is plane or it's like a sheet, for sheet or line charge, Gaussian surface is cylindrical. Gaussian surface is cylindrical. So these are the criteria to choose a Gaussian surface. But if you remember this thing, that if you have a spherical charge distribution and you use a spherical Gaussian surface, then that spherical Gaussian surface will automatically satisfy all these three conditions. Or if you have a sheet or a line and you use a cylindrical Gaussian surface, then that cylindrical Gaussian surface will automatically satisfy all these three conditions. This we will see in the next derivation. Just please note it down. We'll start with the first application. Jubaina, Fatma. So let's solve the first application, electric field. Electric field due to infinite plane sheet. Infinite plane sheet. So Afroza, which charge density you would use for infinite plane sheet? For infinite plane sheet, you will use linear charge density or surface charge density or volume charge density. Which one is the most appropriate charge density for infinite plane sheet? Surface, volume, or linear? Afroza. Volume. Jubaina. Which charge density would be?
Surface.
Surface. Sheet is two-dimensional, Afroza. If I am taking a sheet, the sheet is a two-dimensional figure. So the most appropriate charge density for sheet is surface charge density, not volume charge. So the charge density is sigma. Volume charge density we can use for a cube and even for a cuboid, or for a sphere we can use volume charge density. But for a sheet is a two-dimensional figure. For sheet we will use surface charge density. So you are supposed to calculate electric field due to this sheet. You are supposed to calculate electric field due to this sheet. So what should be the shape of Gaussian surface for the sheet? The appropriate shape of Gaussian surface for the sheet?
Cylindrical.
For a sheet, it's a plate. The Gaussian surface should be cylindrical. For sheet, Gaussian surface should be cylindrical. The Gaussian surface should be cylindrical for the sheet. So let's consider, and the area of the ends is this. Consider a cylindrical Gaussian surface, having area of ends. So we take a cylindrical Gaussian surface and the area of ends is this. This sheet will generate electric field in this direction as well as in this direction. The direction of field is away from the charge. So this sheet will generate electric field to the right hand side as well as to the left hand side. So the first step of the calculation is, using this electric field, you are supposed to calculate flux through the sphere. I'm repeating it again. You have a sheet having an infinite plane sheet. Infinite plane sheet means the dimensions of these sheets is infinite. The length and breadth of the sheet is infinite. Some charge sigma is uniformly distributed over the sheet. You are supposed to calculate electric field E due to the sheet. To calculate this field using Gauss law, the first step is you have to choose an appropriate Gaussian surface. So if you have a sheet, the most appropriate Gaussian surface is cylindrical. So we choose a cylindrical Gaussian surface for the first step. The next step is we have to calculate the flux through the cylinder. Now to calculate flux through cylinder, we divide cylinder into three parts. First end, second end, and the curved surface. So Fatma, what should be the direction of this end one of cylinder? This plane, say if I'm saying this is the cylinder, I'm asking the direction of this particular end. Fatma, what should be the direction of this first end of the cylinder?
Right side.
Right side. The direction of area is perpendicular to the area, so this is right. So flux through end one. So the flux through the first end of cylinder, which is phi 1, is simply E dot S. E and area vector S are acting in same direction. So we can write this phi 1 as, this is ES cos 0. So the flux through the first end is ES1. That's first equation. Jubaina, what should be the direction of this second end of cylinder?
Left side.
Left side, very good. This is the direction of this second. Flux through end. So through N2, we can write flux phi 2 as, this is ES cos 0 again. Then your flux is ES1. That's second. Afroza, through this curved surface, what should be the direction of the curved surface? Afroza, what should be the direction of the closed surface? This is closed surface. I'm considering a small element ds here. What is the direction of this ds? Is it to the right hand side, left hand side, upwards? What's the direction of this ds? Afroza. Afroza, did you get the question? Afroza. Anyone else will try? Fatma, Jabana, can you guess the direction of this ds?
Upward.
Upwards. It's always perpendicular to the area. Afroza, are you getting me? Are you hearing? Can you hear me? Afroza, am I audible? Is having internet problem. So this is the direction of n cap. So if you consider the curved surface, then your flux through the curved surface.
Sir, why will it be?
Yes, Fatma.
Why will be the direction upwards for the curved surface?
The direction is always perpendicular to the surface. If this is the surface of the cylinder, then the direction of the surface should be upwards. If I'm considering here, then the direction would be downwards. If I'm considering something on the front side, this portion of curved surface, it would be outwards. It's always perpendicular to surface. So through the curved surface, this integral will be E ds cos 90. Cos 90 is 0. So the flux through the curved surface will be 0. That's the equation. So we can calculate total flux through cylinder. So the total flux through the cylinder is phi1 plus phi2 plus phi3. So the phi1 is 0, not phi1 is 0. Phi1 is ES, phi2 is ES, phi3 is 0. So the total flux through the cylinder is 2ES. That is the equation. Is it clear? Yes. Okay. So the total flux through the cylinder is 2ES. The next is, we will also calculate this flux using Gauss Law. We can even use Gauss Law to calculate this flux. We can even use Gauss Law to calculate this flux. So using Gauss Law, the flux is Q enclosed by epsilon naught. So this is an infinite sheet, a very, very large sheet. Can you guess what portion of the sheet is cut by this sphere? It's a very large sheet and I'm just passing a cylinder through this sheet. Can you guess the portion of the sheet or the area of the sheet cut by this cylinder? This is my sheet. I'm passing a cylinder through the sheet. Can you guess the area of the sheet which is cut by the cylinder? Or the area of the sheet which is inside the cylinder? Fatma?
Sheet minus area of cylinder.
I'm asking the area of sheet which is cutted by the cylinder, not the remaining area. The area of sheet which is cut by the cylinder, or the area of sheet which is inside the cylinder.
Is it area of circle?
Area of circle, right? So it should be basically this portion. This much of portion, right? It will cut an area which is corresponding to the area of ends. And the charge over this portion is Q enclosed. Because Q enclosed is the charge inside the cylinder. Charge is distributed over the sheet. So the portion of sheet which is inside the cylinder is this S. This area S of sheet is inside the cylinder. So you can say that Q enclosed here, Q enclosed is charge on area S of sheet. So Q enclosed is simply the charge on the area S of sheet. Is it clear? This particular statement, Q enclosed in charge on area S of sheet. It's clear.
Yes, sir.
Okay, just write up to this last point. So here you can write sigma is charge upon area. So sigma is simply Q enclosed divided areas. You can write Q enclosed as sigma S. If I say that this is equation number 5 and this is equation number 6, then we can simply substitute 6 in 5. We can easily substitute 6 in 5. If we substitute 6 in 5, then your 5 will be it's sigma S over epsilon. This is sigma S over epsilon naught. So this is equation number 7. Now see, from equation number this 4 and equation number 7, we are getting same flux. Just the approaches are different. In equation number 4, we calculated flux through the cylinder. Even in equation number 7, we calculated flux through the cylinder. Only the approach is different. But we're just using different approaches. Here we have used the concept of electric field, and here we are using the Gauss Law. So 7 and 4 are same equation, so we can equate. We can simply equate 7 and 4. If we equate 7 and 4, then we'll get 2Es is sigma S by epsilon naught. This S will cancel this S, and this E comes out to be sigma by 2 epsilon. E comes out to be sigma by 2 epsilon. So this is electric field due to an infinite plane sheet. Afroza, from where you left the meeting? From which equation you left the meeting? From starting only. Okay. See, Afroza, we consider an infinite plane sheet. Okay, no problem. We have considered an infinite plane sheet. We are trying to calculate electric field due to this sheet. So we first consider a Gaussian surface, cylindrical Gaussian surface. The area of the ends is S. Now we have to calculate the flux through this Gaussian surface. To calculate flux through this Gaussian surface, we consider the direction of this area vector, which is outwards, rightwards. This is electric field E. So through N1, flux through N1. So through N1, flux is phi 1, which is simply ES cos 0, which is ES. Since area vector and electric field are acting in same direction, that's my first equation. The next, we calculated the flux through the surface 2. Flux through N2. Flux through N2. So for N2, the flux is ES cos 0. The direction of N2 is again away from the area, perpendicular to the area. It's along the field again. They are parallel. So this is again ES. That is equation number. After this, we calculated flux through the curved surface. For curved surface, the direction we consider a small element ds. The direction is upwards. So the angle between area vector and field is 90 degrees. So we calculated flux through the curved surface, which is EDS cos 90. This is 0. Then we calculated total flux through the cylinder, which is sum of all. So ES plus 0. So that comes out to be 2ES. Then we use Gauss law and write that flux is simply Q enclosed by epsilon. The next task is to calculate this Q enclosed. To calculate this Q enclosed, see, the charge is distributed over the sheet. So the Q enclosed is the charge of sheet which is enclosed by cylinder. The charge of sheet enclosed by cylinder. This cylinder have enclosed area S of the sheet. Since the cylinder is passing through the sheet, the cylinder cut an area of sheet which is equal to the area of ends of cylinder. So this cylinder cut an area S. So this Q enclosed is basically area of charge on area S of sheet. So we can write this sigma as Q enclosed by S. So Q enclosed will be sigma S. We just substituted the value of this sigma S here. So phi is simply sigma S by epsilon naught. So we can now equate 4 and 7. So this is 2ES is sigma S by epsilon naught, and this is E, which is sigma by 2. So this is electric field due to an infinite range. Please note it and let me know when you have written. Fatma and Jumana, clear? Okay, I will stop here today. I need just 1 hour class for to finish this chapter 1. It's tomorrow have a 1 hour lecture from 10 to 11. Tomorrow we'll finish this chapter so that from Saturday onwards we can start chapter number 2. Let's stop here. We'll continue tomorrow. Tomorrow at the same time, 10 to 11. Okay. Love this. Okay, but